Just check.
Mr. Edie, did you watch Pat and Sam on TV last night?
Yes?
They were on TV.
Yeah, I know, I saw him. Congratulations.
I know people on TV.
Before we get started, we have new students. This is Alexis, right? Is that right? Lexi? You go by Lexi?
Yeah.
Right. This is Lexi. She's new.
Where are you from?
Originally Chicago, but I don't really stay here very often. So
She lives in a tanning booth.
it was colder there than it was here.
Oh, hold on, everybody. It was cold.
Wait,
Oh,
how?
no.
It was like 60 in Denver.
It was like 55 in
Oh.
Arizona. And like
Oh,
30
that's
How does that
so
happen?
horrible.
Global warming.
I need a moment. Oh, I feel so bad for you. Wait, I'm over it. Okay, volumes now. So we're going to take all these goofy shapes that we've been working with for the last 2 days and start spinning them around axes. We're actually going to do two methods today. We're going to do the disc method and the washer method. Well, you'll see. Patience. Why not?
Someone said the washer method.
I'm sorry?
Someone told me the washer method was the worst part of calc. But I don't know if that's true.
Oh, no, it's not.
Oh, okay.
Oh, I got the worst part of calc coming, but it ain't the washer method. It's not today, though. I'll let you know. I'll let you know ahead of time.
You can bring your Kleenexes in.
Okay, so we're gonna take a figure, an area, a bounded region, whatever you want to use it. We're gonna spin it around an axis, and sometimes those axes will be the x-axis, the y-axis. Sometimes it'll be the line x equals 4. Sometimes it'll be the line y equals 4. What we aren't going to do is revolve things around non-horizontal or vertical axes. That would be too nasty. Okay, so nothing gets revolved around the line. Let's say y equals x. We'll just keep it. We'll use the KISS method. Keep it simple, students. Then we'll talk about the washer method, and you should give 2 hugs today. Not now. And not me. There's our representative rectangle. I blew up our representative rectangle so we can see better what's going on, because the representative rectangles that we used have 0 thickness. This one I gave some thickness and called it W.
Infinitely small.
What?
Is it infinitely small or is it 0?
Yes. Yes.
Why did you choose a K instead of a C for the disc?
Because that's how you spell disc.
No, you can spell it both ways.
I think there's a big
Sam,
difference.
you're getting closer to fighting. Every day, another step closer, Sam. Until, like graduation, you're going to be walking across the stage, and I'm going to be coming out of nowhere, tackle you right off the stage, which would be awesome. You're sitting there like going along.
Just get close.
The A's, the B's, and you get to that point where it's starting to get boring because now you're in like the K's and the L's, and then the R's come up, and it's go time. Okay, so as we talked about the other day, if I take that little rectangle and I spin it around what's called the axis of revolution, I create something called a disc. Our discs, however, are going to be very skinny, more like a quarter instead of that giant
Cheese.
ding-dong looking thing.
It's a cheese.
You guys know what ding-dongs are?
Yeah.
Yeah.
No?
Yeah.
For candy.
No.
They're
They're pastries.
yeah, it's a little cake thing that's covered in chocolate.
It's got cream filling.
They're quite delicious. So when we did area, we found the area of one rectangle and used the accumulator, aka the integral thingy jobber, the Archimedes symbol, to find the area by adding up all those rectangles. We take that idea and expand it into volume. If I can find the volume of one disk, I can use the accumulator then to add up all those disks, and you got the volume. So far, so good? Awesome. Yes, Sam?
Why can't you just do like the radius? Like treat it as a cylinder?
It's funny you should ask that question, because I was going to ask you the following question. Sam, what's the volume of that disk?
squared times W.
Beautiful. Let's give it up, huh? So we're actually going to do the same thing, right? Instead of W, however, we're going to use dx or dy, depending on what shape we're working with. Find the volume of one of those, and then integrate it over the whole thing. Okay? And yes, it's just that simple. So, like Sam said, pi r squared W. Now, why a capital R? Again, knowing where we need to go and where we're going to go, we will have two different radii in the future. We'll have a capital R and a lowercase r. So I want you to get used to using the capital R for now. Okay, so this is just geometry so far, right? We good? Any problems? I'm sure you all excelled in geometry. Some more so than others.
You know how it sounds.
It's too easy, I'm just going to let it go. Okay, so that's what we're going to do. We're going to build shapes by stacking a bunch of rectangles. And there's a bunch of notation in there that we don't care about, delta x, dx, blah, 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 blah. Not a very pretty shape. How do I get the shape prettier?
More rectangles.
Smush it. How so, Kev?
I don't know.
You just like the word smush?
I mean, makes sense too.
Okay.
More infinity.
More infinity. What does that mean?
So like more rectangles.
More rectangles. Right. And we've talked about this before. More rectangles or skinnier rectangles results in the same scenario. If you increase the number of rectangles, the width of the rectangles shrink. If you shrink the width of the rectangles, the number of rectangles shrink. Till eventually we have rectangles that have a width of 0 and how many rectangles? Infinity. Beautiful. See, then we want a pretty shape like this blue guy, not this big honking weird stacky thing with discs. So we're going to shrink that delta x. Yeah, we just did this. Okay, good. We know that. Oh, hey, watch this. This is fun. Hopefully I can get it to work. No, go back. Okay, great. Let's try once more. Because if it didn't work once,
Third time's the charm.
no, it's not really. What class is this? Calculus. Thank you. Get over here. Okay, so even though this is going the wrong way, you can still see the idea here. So what I got here is a little rectangle. Our rectangles will normally be, at least for tonight, they'll be vertical rectangles. But again, if you don't believe me, if you take that thing and you spin it around an axis, it generates that little disc thing.
Cheese wheel.
Yeah, the cheese wheel, if you will.
I didn't believe it till I
Thanks,
saw it.
I didn't believe it till I
It's just mesmerizing.
What we're going to do, however, is take functions like this and find the volume. So right now you can find the area of that shaded region. We want to expand that and be able to find the volume if I take that nice simple function of the square root of x and spin it around the x-axis. So if you spin one rectangle, you get that disk we talked about. And then you spin them all, and we stack that into that little weird thing, shaped thing. It'll get worse later when we start looking at all kinds of different shapes. Like, for instance, what happens now if this isn't the axis of revolution? This is now the axis of revolution. What happens when I spin this?
There'll be a little hole in it.
Get a hole in the middle.
There's a hole in it. You know what's up.
So you get that hole through there. And we're going to be calculating those volumes. We're going to be calculating the volumes not by, like in geometry, you would calculate the volume by finding the volume of the outside thing and subtracting the volume of the hole in the middle. We're not going to bother with that stuff. We're going to calculate the volume directly.
But you said it's an algorithm, so you can, it's basically the same for everyone, just a little tweak
Yes,
based on
we'll
what-
go with that, sure. Okay, so here's our first example. We're going to take a nice pretty parabola, x squared plus 3. That's simple. It's a parabola shifted up 3 units. And we're going to bind it. We're going to make it a bounded region by binding it between -2 and 2. And then spin that puppy around the x-axis. Okay, so I'm going to give you a series of questions that you can use to talk yourself through the process. And like the area, when you start this, it's going to seem silly to ask yourself these questions over and over again. But as we accumulate, no pun intended, more types of problems, these questions will become relevant. So question number 1, are we working with a vertical or a horizontal rectangle, representative rectangle?
Vertical.
It's vertical. So therefore, are we working with x's or y's? X's. Beautiful. Is the representative rectangle perpendicular to or parallel to the axis of revolution? Perpendicular. Good. And that's all you're going to see initially. So the answer will always be perpendicular. The big question is the representative rectangle touching or not touching the axis of revolution? Touching. It's sitting on top of the x-axis, which is what it's going to spin around. If you go through that questioning process with yourself, you reach the final solution that this is going to be a disk method. And since we have no other method, we're always going to get a disk method until I show you a different method, which is the washer method. Okay. Vertical rectangle working with x. Perpendicular to the axis of revolution. That means it's going to be a disk or a washer, not something called a shell that comes later. It's touching the axis of revolution, therefore we have a disk. And as Sam already told us, all we need for that problem then is what? The volume of the disk, which is?
The height, or well, the radius times the width.
Good, and what's the width?
Isn't it the from where to where? So.
But in this case, what are we going to use for a width?
Oh, -2 to 2.
No. Remember, we're only talking representative rectangle. This rectangle right there is how wide? Pat? dx. We want it really skinny. Okay. How tall is it, Sam?
Yeah.
No. See? It doesn't matter what they say. Chickens.
Oh, is it R?
Good.
No.
The radius for our disk is the same as the height of that rectangle. We did the height of the rectangle yesterday and the day before. How do I find the height of that rectangle, Sam?
You take the integral. I don't know. I mean, what is
Top minus bottom.
oh, top minus bottom.
Top minus bottom.
Gotcha.
Yeah. And the top is?
X squared plus 3.
The bottom is?
X equals the x-axis. So,
Which is?
y equals 0.
Good. Okay. So is everybody following that? The radius of our disk, in this particular case, is the same thing as the height of our rectangle, which we did with the area. And so as we progress through this, you'll see how these pieces start to fit together. So we need to find the volume of, it's a little hard to see in the picture, but the volume of that one little blue disk in there. If I can find the volume of that little blue disk, which we can, because Sam just talked us through it, then all we need to do is set up an integral. And that integral is going to go from what to what, Sam?
-2 to 2.
Perfect. Okay. There's our area of the rectangle. Okay, that's the height times the width. Spin that. Plug into the volume formula for a disk. Okay. Square it, multiply it by pi, and multiply it by the thickness. And we have the volume of one disk. This is the hard part, getting to here. The rest is easy peasy. Now you just set up an integral. And as we already mentioned, it's an integral from -2 to 2, and it works itself out. I fn-inted that. That's hard to say. But let's pretend you weren't going to fn-int. Notice what I did. I moved the pi out in front. Why would I move the pi out in front?
Constant.
Sam? Murray, why would I move the pi out in front?
It's constant.
Good, it's constant, it doesn't matter. So do all my calculus inside. How do you take the antiderivative of x squared plus 3 quantity squared?
Squared out.
Dennis?
U to U? No, never mind.
Why not a u to u?
Because the X will go away.
Uh-huh.
Couldn't you just like factor out like X to the 4th and then do it like that then?
Good, multiply it out.
Yeah.
If we had another term in there, if there was, let's say, an x in there, then you can do a u to u, but you hit it on the head. The x's won't cancel, so therefore you gotta multiply that out. Take the integral of each individual part. Plug in -2, plug in 2, plug in -2. Okay. Let's talk a little bit about the process. Is everybody following what's going on here? Now, if the area problems blew you out of the water, this stuff is going to be difficult because we didn't lay a good foundation for how this is going to work as far as finding the area of the rectangles and things like that. Still top minus bottom, that still comes into play. It's just we're using the top minus bottom in a different capacity here. Here we're using it as the radius of that disk that we're creating. Okay, should we try another one? Let's see what else happens. Okay. Now we're going to change one small thing. We're going to go through the same process. We have a vertical representative rectangle. It's perpendicular to the axis of revolution. However, this time it's not touching. So the one we did with the hole in it is what we're going to figure out using a washer method. Therefore, we don't have a disk anymore. We have a washer. It's got a hole in it. Just like if we took that other thing that I spun before and chopped it into pieces, each one of those pieces would be a washer. Pregunta.
Can you say again what were like the questions you asked, just to see which method it is?
Are the representative rectangles horizontal or vertical? If they're vertical, you're dealing with x's. If they're horizontal, you're dealing with y's. We're only doing x's today. Is a representative rectangle perpendicular to or parallel to the axis of revolution? We're only dealing with perpendicular right now. We'll get to parallel later. Is it touching or not touching the axis of revolution? If it's touching, it's a disk. If it's not touching, it's a washer. Good? Okay. New formula now. Finding the volume of a washer involves having two different radii. You have the outside radius, which is capital R, and you have the inside radius. When you're working through these problems, capital R will always be the farthest distance from the axis of revolution to a point on the rectangle. And I'll show you this in a second, what I'm talking about. Capital R is the closest distance from the axis of revolution to any part on the representative rectangle. Here's my axis of revolution. Here's my representative rectangle. Where's the farthest distance? It's going from the axis of revolution up to the top. That would be capital R. Where's the closest distance from the axis of revolution to the bottom of the representative rectangle?
Can little r change within the washer?
Yes, but we don't care because the integral takes care of all of that.
It will accumulate everything based on the equation.
Yep. So if you have a function that's not going to generate a horizontal, let's say you have a sine graph.
Yeah.
The bottom of your region has a sine graph on it. It'll be taken into account with the integral, so you don't have to worry about it.
Because that's what I was wondering on like the disk, because if you have like, because the x squared plus 3 is gonna take the whole equation, even
Yeah.
if it's a different size, then,
Yeah, the height of the rectangle changes when you go from -2 to 2.
but it's all in the equation.
It all works out in the integral, so we don't care. Big R is farthest distance from the axis of revolution,
Wouldn't
basically from the axis of revolution to the top of the
Why
road.
would it have a different radius?
Because you have a radius for the outside and you have a radius for the circle
Oh,
inside.
okay, I see.
And then you subtract. Notice this formula. It's not a common mistake that people make. It's not capital R minus little r quantity squared. It's each of these squared. In other words, what I'm doing is I'm finding the area of the whole disk and subtracting the area of the little circle in the center. Is anybody's brain melted yet?
And W's just dx.
dx, correct. So now we start doing weird things like this. We take this nice pretty little sliver thing, which, I mean, you could easily generate that sliver, maybe take a big wide parabola, put a line through it, and you get that little sliver. And now we spin that. And when you spin it, you get one of those weird things.
Little lamp. Little lampshade.
Yeah, but it'd be like a fat lampshade.
Yeah.
You know, most lampshades are one piece of fabric. This have like a,
Thicker, yeah.
like maybe some fancy decoration on the inside. And if we wanted it to be a lampshade, like a real lampshade, then we'd have to work in terms of Y and spin it. That comes later.
I don't
We're
even
just
think
drinking
it's
that.
getting flipped over.
We good?
What axis is it getting flipped over there?
This one.
Oh,
Another example. So here's a weird area. And again, we don't care what shape the area is. I don't even know how to describe that other than it's pink. F of x minus g of x. You get a representative rectangle in there, which is over here, and just spin that puppy and we get the washer. Add up all those washers and you get that weird looking 3D.
rubber stopper.
Why would a rubber stopper have a hole in it?
There's a hole in rubber stoppers.
Yeah.
But
Then
they're
they
like,
don't stop.
they're like really mini, but there's still holes in them.
Then it's not a stopper.
No.
It's a slower downer.
Yeah, but the gas is.
So rubber slower downer.
Yeah, rubber
Okay.
slower down.
What would you use a rubber slower downer for?
To keep gas from effusing.
Or if you
Through
want to
the hole?
slow down more.
But it will.
No, it won't.
There's a hole in it.
Going through a hole.
We'll go. The rubber stoppers had tiny holes in them. I swear.
Anybody else? Oh, is this AP Chem you're talking?
Yeah.
Anybody else in AP Chem? Do the rubber
They have
stop?
holes in them,
They
yeah.
do
They do
have.
have a hole they can put the tube in.
You're like really
And the picnometers.
Really
the
not how I
picnometers
was figuring that
have
would work out.
Yeah, but like,
You put the
it's
tube
cause
in
like
to
so it
measure
doesn't
it.
explode when you pull it out.
We did that already. So we don't need to go back to that because I showed you already what happens when you spin something off the axis and get that weird looking
Rubber slower down.
rubber slower downer. Okay, so there's the formula again. It's the same one. Okay.
So scary.
Big radius squared minus little radius squared times the thickness, which is always going to be dx or dy. Move the pi out in front. The pi plus this stuff is just the volume of one washer. And then you add up all the washers from A to B. Done. Not going anywhere, just clicking to show you that. Eventually, it might be a good idea for us to kind of build a hierarchy here of, so especially for those of you that are visual learners, starting from the question stuff and where it leads. Okay. Starting with a simple question of vertical or horizontal rectangles. If yes, go this way. It's like a choose your own adventure. If yes, go this way. If no, go that way. If yes, go, and then ask the next question. Eventually, you end up with finding out it was the guy that owned the amusement park that actually started the fire. Wouldn't got away with it if it wasn't for you kids. Anybody? Scooby-Doo?
Scooby-Doo.
All right. I didn't know if you guys were I'm sorry?
You meddling kid.
meddling kids, right? Thank you.
Is there?
And
volume
dog
on
too.
the quiz
Yeah.
Tomorrow.
Meddling kids and dogs.
Quiz is
too.
Friday or Monday.
Oh, so there wouldn't be volume on.
Monday.
Here's the lampshade without the hole in it, so that's the same cat's eye / leaf thing we did yesterday. But when you spin it, you get that thing, whatever you want to call that thing. Pat, what would you call that thing?
That protects your fingernails. It's one of those little,
Yeah,
Very
it's kind of
little.
like to turn pages of something.
like a
I literally don't know what to say.
like a really thick.
It's a very like a weird
I got
shape.
nothing.
It's a pinky cap. It's a pinky cap.
Then why's it pointing?
Outer radius, capital R. What's the furthest distance from the representative rectangle to the axis of revolution? Inner radius. What's the closest part? So if I go back to the picture here, and you can see these in the actual picture. Here's my representative rectangle. It's a little fat for my tape, but that's okay. Here's capital R from the axis of revolution up to the furthest distance. So that takes me up to that function, and that function is the square root of x. Where's little r? Little r is the shortest distance from the axis of revolution. That goes to that function, which is x squared. So now I know capital R, I know lowercase r, put it into the formula. And this is after going through the whole process, which I'll take you through again, and you're going to be tired of hearing about, but I guarantee it'll help you. Vertical or horizontal representative rectangles?
Vertical.
Vertical. So we're working in terms of x. And that's the first path in choose your own adventure. Is the representative rectangle perpendicular to or parallel to the axis of revolution? Perpendicular. Therefore, we're using a disc or a washer. Is it touching the axis of revolution? No, so therefore we have a washer. And if it's a washer, it's big R squared minus little r squared times pi integrated over the interval.
So
Oh, never mind.
You good? Okay.
how do you get big R there?
Farthest distance from the axis of revolution.
Well, how do you find it?
It's the function.
Oh,
Farthest distance is this, and how do I get to that? I go up to that function. Here's the shortest distance. How do I get it? I go to that function. And then you got to solve that puppy. Multiply it out. Fn int it. Whatever works for you.
Sand.
Probably not too bad to solve by hand. What's the square root of x squared? X. What's x squared squared? X to the fourth. Both of which you can find the antiderivative of. There's nothing incredibly nasty there. Take the antiderivative, plug in 1, plug in 0, subtract. Don't forget to multiply by pi. And if you're looking to give an approximate answer, the standard is to use the pi button, not 3.14. You should know that, but I thought I should just say it just to make sure we're all on the same page. It does make a difference when you're rounding to 3 decimal places. I'd hate to see you not get credit because you used 3.14 instead of that stupid pi button. Okay, yeah, so then I multiplied it out, took the antiderivative of each, plugged in 1, and there's kind of a big jump, but plugged in 1, got a nice answer. Plugged in 0, which didn't matter at all because it gives me 0. Multiply my final answer by pi. There's the exact answer, 3 pi over 10, or a decimal equivalent answer, plugging that into your calculator, getting something like 9 point something or another. No, 0.9 something or another. Abby, do you have a question or are you just stretching? Okay. Okay, we good? All right. Well, we'll see. Let's make it more interesting. Do we just need like a 2-second breather here?
I thought we did this one.
Okay. Oh, no, we didn't. So far, let's review. We've had the axis of revolution touching the x-axis. We've had the representative rectangle touching the x-axis. We've had the representative rectangle not touching the x-axis. But now, let's spin it around something that's not the x-axis.
Top minus bottom of that function.
Still top minus bottom, right. We're not going to do y-axis today. We'll do that later. So we'll do that guy. I'm going to spin that gray region around, I forget what I'm spinning it around. Around the line y equals 3, which is up here. So just take a second to visualize try to visualize what that thing would look like if you spun it around that line. The outside would be nice and squared off, the inside would have that little funky shape thing inside
But
there.
it would be kind of like
Yeah.
a lampshade.
It's a cheaply made pinky cap.
Kind of a trapezoidal,
Yeah.
right? With almost maybe kind of a sphere in the center of it.
Well, like like a little Hershey kiss in the middle.
Kind of looks like the.
And none of that is relevant. I'm not gonna ask you to draw these 3D shapes,
Well, like a shape out of your
but I am gonna ask you to calculate the volumes. And it goes something like this. Let's see, who's feeling? Sid? Feeling saucy? You can do this, right?
We'll try.
We'll help you.
Okay.
Okay, vertical or horizontal axis, or, sorry, I gotta ask the right questions. Hey Sid, vertical or horizontal representative rectangle?
Vertical.
Are we working,
Oh, yeah.
because it's
Oh, yeah.
oh,
Yeah.
what is that, a private mark?
They're private.
Oh,
Yeah.
okay.
Let me see. Like that.
I thought he was really excited about your answer. Oh, yeah. Where were we? Vertical, so we're working in X or Y?
I don't know about
X.
X, perfect. Is it perpendicular to or parallel to the axis of revolution? Good, which means it's either a disk or a washer, right? Is it touching the axis of revolution?
Yes. In the corner.
Remember, we're only talking about the representative rectangle. Yes, it is touching up there in the corner, but is the representative rectangle touching the axis? No. So therefore we have a washer. Okay, good. Which means I need capital R and I need lowercase r. Right? Okay. Capital R. Here's my axis of revolution. Here's my axis. Here's. How about that women's hockey team, huh? Okay, here's that axis of revolution. Capital R would be the farthest distance on this representative rectangle. Therefore, that would be capital R. Where's lowercase r? It's the closest distance. That guy. Let's stop and take a breather. Everybody okay so far?
No.
You follow me? No?
Why is the representative rectangle vertical?
Because that's what I chose it to be.
Could you have picked it to be horizontal?
Oh yeah, but then that would be that'd be horrible.
That's shell method.
Okay, now why would it be horrible? Because number one, we haven't talked about horizontal rectangles with volumes of revolution. Number two, you'd create something called the shell, which we haven't covered yet. Number three, you'd need three different representative rectangles because the right and left change as you move down that figure. We can do it that way if you like.
Yeah, Pat.
I'm just not going to. So you just sit there and be quiet now. Alright? Okay. No, it is possible to do it that way, but it'd be a different way to do it. Okay. Everybody else good? We're almost there. We just need 2 more chunks of information. 3 more chunks of information. First chunk of information. What is capital R? Or, Allison, how do I find capital R? Correct. And it's marked there. So how do I find that length? How do I find this distance from here down to there? Good. What's the top?
X squared plus 2.
Mm-mm.
The top of the line? Oh, so X equals 3.
Y equals 3, right. So 3. Where's the bottom?
X, when I have X equals 3.
Good. Okay, so there's capital R. Capital R is 3 minus, don't forget parentheses. Allison, you're almost done. What's little r?
So it would be y equals 3 and then X squared plus
Good. We only need one more chunk of information. I'm taking rectangles from where to where. In other words, what are my limits of integration, Allison?
0 to 1.
Perfect. Put that all together, we're done. So, the volume, don't forget to label it as a volume because we've done area and volume, so you need to distinguish. I'm going to put the pi out in front because it doesn't matter. As she said, we're going from 0 to 1, and the formula for a washer is capital R squared, so I take this mess and square it. Be careful with parentheses. Whoops, not that. Minus little r squared. What did I forget?
DS.
Dx. Good.
I'm assuming we'll have a calculator for this.
I wouldn't assume that.
That's good for you. It builds character. Puts hair on your chest.
Should we square one of those just for giggles? Just to make sure everybody's good?
Yeah.
Okay.
Just
Let's do a little sidebar here. What's that equal to?
X squared plus 4x.
Shh, Cameron, be quiet. Ella, what's that equal to?
X squared plus 4x plus 4.
Square the first term, multiply two together, double it, square the last term. Beautiful. So if we take this, what was it, x squared?
You can multiply.
1/2 x plus 1? Okay, plus 1 quantity squared. What's that? Square the first term. Multiply the two terms together, double it. Square the last term. Oh boy. That's fun.
Are you
Oh
done?
wait, now you gotta square another one inside of that.
Or you could just add like terms in the first place.
Did you mean 3x?
What did I do wrong? 3x, yes I did. Is that better? Oh boy, that's fun.
Why didn't you just subtract the 1 from the 3?
Could have done that too. Yeah, that would have been a lot easier. This was more funner though. Yeah, you could have done -1/2 plus 2.
I wouldn't have.
That would have been a lot easier.
I didn't even know you could do it that way.
Nah, you've learned something good, so my goal as a professional educator is accomplished. There it is. Is that what we had? Beautiful. There we go, yeah. We're done. Okay. So much